This will be a brief learning lesson to review conceptual math knowledge. This slide includes a visual representation of the concept of the domains of math knowledge. As a review, at the base, you will see declarative knowledge. This is knowledge like basic math facts, vocabulary, and any other background knowledge students have that they can automatically recall. It could include the fluent identification of numbers, shapes, and symbols as well. I have these at the foundation because students need automaticity with this kind of knowledge in order to apply it to new, more challenging information. Problem solving is the top of our structure because it is the ultimate goal of all mathematics. Why calculate anything if it isn't applicable to a real-life situation? The pillars are conceptual and procedural knowledge. I made them pillars to help you remember that students must build these equally in order to support problem solving. If we only build conceptual understanding without knowledge of how to apply that understanding, we won't be able to problem solve. Likewise, if we blindly follow procedures, we may be able to solve that particular problem, but we won't be able to understand why we use those procedures, and thus we wouldn't be able to generalize them to other problems. We use scaffolding to help temporarily support students as they build these pillars. It is important to note that declarative knowledge generally starts out as conceptual knowledge, so there is a constant flow from the conceptual pillar to the declarative foundation. For example, before students memorize that 5 times 2 equals 10, they need to understand the concept of multiplication to mean equal groups. In this case, 5 groups of 2. Eventually, that concept of multiplication is so fluently applied to more challenging problems that it becomes part of declarative knowledge. Remember also that for struggling students, declarative knowledge often has cracks, so we need to accommodate for those students when they're working on grade-level tasks, and we should remediate by providing review instruction during Tier 2 or Tier 3 instructional time to help repair those cracks. In your textbook, the authors describe 5 different ways to model concepts. I thought it would be beneficial for you to see the same concept shown in these 5 different ways. Please note, not every concept is a good fit for each of these categories. You should pick multiple representations, and you should pick ways that make the most sense. Let's look at the concept of identifying and categorizing quadrilaterals. Quadrilaterals are polygons with 4 sides. If you are unfamiliar with the definition of a polygon, it is any closed shape with all straight sides. In this first conceptual model, I'm showing you 4 different categories of quadrilaterals using a compare-contrast visual. If I look across the rows, I can see all quadrilaterals have 4 sides, 4 angles, and 4 vertices. I can see that only in the square and rhombus are all 4 sides equal in length. Rectangles and squares must have all right angles, whereas a rhombus might have right angles, but it might not. A trapezoid will never have more than 1 right angle. Sometimes it has none at all. That was just one way to present the information. You also may want to present this concept in a transformational way. Start with a non-specific quadrilateral like this one. If I manipulate or transform that non-specific quadrilateral so only one set of sides is parallel, it becomes a trapezoid. I could transform it again so now both sets of sides are parallel and it becomes a parallelogram. By doing this, opposite side lengths become equal in length, which is another characteristic of a parallelogram. One way I could transform the parallelogram is to take it and shrink one set of the sides so all sides are equal in length. This would make it a rhombus. Or I could take that parallelogram and keep the side lengths the same, but just tilt it so all of the angles are right angles. This would turn my parallelogram into a rectangle. Then I could either take that rhombus and tilt it to make all right angles to get my most specific quadrilateral, the square, or I could take my rectangle and shorten the long sides so all sides are equal, and that would also make a square. This transformational model works really nicely for this concept. You could even have students make these shapes with manipulatives like pipe cleaners or wiki sticks for a hands-on approach to modeling transformation of quadrilaterals. This hierarchical model might look the same as the transformational model at first glance, but its purpose is a little different. The most general quadrilateral is at the top, and the most specific is at the bottom. Notice the direction of the arrows in this diagram. I can follow along any path to see the relationship between these shapes. For example, this model shows that squares are also rectangles, kites, parallelograms, and rhombi. A square meets all the criteria for those quadrilateral shapes. However, looking at the direction of the arrows, I can see that the inverse is not necessarily true. All squares are rhombi, but all rhombi aren't necessarily squares. This model is nice to show three distinct types of quadrilaterals: kites, parallelograms, and trapezoids. Kites are quadrilaterals with two pairs of equivalent adjacent sides. So these adjacent sides are the same length, and these adjacent sides are the same length. Both a rhombus and a square fit that definition too. So they are also kites. The square is the most specific example of a quadrilateral, and a square is also a rhombus, a rectangle, a parallelogram, and a kite. This diagram is also a good way to show how trapezoids are not in the main hierarchy of quadrilaterals, because they only have one set of parallel sides. So a square is not a trapezoid because it has two sets of parallel sides. A good practice in math is to use ample examples and non-examples. Sometimes students can learn about a concept by understanding what it is not, just as much as by understanding what it is. The model on this slide is for identifying quadrilaterals, not really for categorizing quadrilaterals, but you could use this technique for categorizing as well. On the left, students can see examples of closed polygons with four sides, quadrilaterals. On the right, students can see the non-examples, so they don't meet that criteria. I could point to specific non-examples and ask students why they are not quadrilaterals. Let's start with these. Why aren't these quadrilaterals? These aren't quadrilaterals because they have more or fewer than four sides, and quadrilaterals must have four sides. Why aren't these quadrilaterals? These aren't quadrilaterals because they have curved sides, and quadrilaterals have to have only straight sides. How about this one? Why isn't this a quadrilateral? This one is not a closed shape, and all quadrilaterals have to be closed shapes with four straight sides. This is the idea behind asking students to look for an error in a math problem as a way of instructing them. Showing them the wrong way to solve it and asking them to correct it can be a valuable process to build conceptual understanding. This final model is less visual and more procedural, though I could add some visuals to go with each step. A student could look at a given shape and ask themselves this series of questions to affirm whether or not it meets certain criteria. Does it have four sides? Does it have parallel sides? How many pairs? Does it have right angles? Are all of its sides the same length? That's a checklist for is it a square? So which method is best? The point is, you should always be using multiple representations of the same concepts to help build conceptual understanding. It doesn't mean every method is useful for every concept, nor does it mean these are the only 5 ways of representing a concept. Sometimes you need to just think outside the box. You do not need to give all of these representations within the same lesson either. This is where assessment of your students and your professional judgment comes into play. When discussing conceptual knowledge, we also have to address the CRA model for instruction. Math can be pretty abstract. When we write math, we have symbols that stand for some concept. The CRA framework for instruction can help students translate from the concrete to the abstract. The 5 models I just showed you were all visual. For students with dyscalculia who may have visual spatial deficits, you may need to begin with something more tangible. That's why I suggest using pipe cleaners or wiki sticks as concrete manipulatives for the transformational model. The C in CRA stands for concrete. Concrete objects are manipulatives like base 10 blocks, fraction tiles, counters, and play money that students can physically touch and manipulate to solve problems. Using concrete manipulatives aren't a fluent way to solve problems, though, but they can help build conceptual and even procedural knowledge. As students become more fluent with the manipulatives, you can move to drawing representations of those manipulatives. So instead of physically moving the manipulatives to show regrouping, I can use circles, arrows, and lines to represent those actions. It's called representational because I'm not physically manipulating anything, and I'm using some symbols to represent those physical items. Showing representations like this is often a great instructional scaffold. Numbers and symbols are abstract. Eventually, we want our students solving problems using our abstract number and symbol system because it's efficient and it's the language of math. We can still scaffold abstract models, though. Look closely at the representational model on the top right and the abstract model at the bottom right. I could use an alternative algorithm like this expanded form method of addition to help translate from that representational stage to the abstract stage. Eventually, as the student understands the concepts of place value and regrouping with regards to addition, they can successfully utilize that traditional abstract model. Here are some considerations for using concrete manipulatives in your classroom. First, you need to match the manipulatives to the task and concept you're trying to teach. You probably wouldn't use base 10 blocks to teach geometry. In your lesson planning process, make sure you plan and practice your verbal explanations of how to use the manipulatives. You should be using explicit instruction when you introduce a manipulative. Model with clear think-alouds, and then let students practice with your support before you have them use manipulatives independently. You have to explicitly plan how to show students the connection between the manipulatives and the paper-pencil representation or abstract task. Don't just use manipulatives one day and the next day try it on paper without helping students make that connection. Allow your students to verbally explain their actions while using the manipulatives. This is a great time to allow your students to be the experts. Have them teach someone else how to use them. Finally, make sure you consider individual needs. A student with a physical impairment or visual impairment may not be able to use the same manipulatives as their peers. They may need virtual manipulatives or some other strategy. Manipulatives also come with logistical considerations. Some secondary teachers think manipulatives are only for elementary students. Secondary math is the most abstract, so manipulatives can actually be a great tool. Oftentimes in secondary education, virtual manipulatives are more common because they seem less little kiddish. Don't forget you need to teach students how to use the manipulatives. You can't just give them to your students and say, here you go, use them. Different manipulatives will be appropriate in different situations. They can add some needed engagement and variety to your lessons. The last logistical consideration I want to mention is to have an organized system of distributing manipulatives. Some teachers don't use manipulatives because they're a burden to manage with large groups of students, so you should think about this ahead of time to make that transition go much more smoothly. Here is one final consideration. As we start leveraging more and more technology in the classroom, we may find ourselves utilizing some virtual manipulatives. Where do you think these fit in the CRA model? They aren't 3D objects, but you can manipulate them. We'll explore some of these in class.